Good morning to everyone. I am Fabio Addona from the University of Bologna, and I'm going to present an experimental study about air-water interaction of paddle waves under wind forcing in the same and opposing direction. The experiments were conducted at the University of Granada in collaboration with the University of Parma. In this presentation, I will introduce the environmental processes involved in the Earth-sea interaction exchanges. Then, the experimental activity will be shown, followed by the results of our data analysis about the free surface elevation and velocity, and considerations about laboratory modeling through dimensional analysis. Finally, we'll report the conclusions supported by our results. From an environmental point of view, exchanges of momentum, gases, substances appear at the Earth's interface involving several scales and variables and influencing relevant issues like climate change. For instance, oceans can highly affect the CO2 global balance by acting as a sink. In order to model and accurately reproduce the evolution of global balance and other relevant subjects like seawater forecasting, it is crucial to get a better comprehension of the dynamics at the Earth's interface. Despite numerous efforts about the study of swell and wind waves and their interaction, results are not exhaustive, and many open questions still remain. In this work, our aim is to study the effects at the interface of paddle waves ruffled by wind in the same and in an opposing direction through an experimental approach. The experiments were performed at the atmosphere-ocean interaction flume of the University of Granada. The flume is capable of coupling several physical conditions such as regular and irregular waves, wind, current, and rain. In our experiments, we used two paddles to generate absorbed regular waves, ruffled by wind in the same or in an opposing direction. The instrumentation consisted of 8 ultrasound probes for free surface elevation analysis, 2 high-resolution cameras for 3D velocity reconstruction in a longitudinal midplane of size 14 by 14 square centimeters through a stereoscopic particle image velocimetry, briefly stereo PIV, and a pitot for measurements of velocity. For the stereo PIV, 2 high-resolution cameras were used with an overlapping zone in their field of view. The cameras take a pair of photograms with a delay of few milliseconds one by each other and a data rate of about 7 Hz. The velocity reconstruction is made by recognizing the distance traveled by the same particles in the time occurred between the 2 photograms for each camera, and by interpolating the obtained velocities over a fixed grid. Furthermore, a stereoscopic view is necessary to obtain a three-dimensional velocity field. 4 different experimental conditions were tested: paddle waves without wind, paddle waves with an opposing wind, paddle waves with a following wind, and wind waves without paddle activation. The regular wave generated by paddles when active was the same for all the experiments, while the wind intensity was changed among the tests with the same experimental conditions. First, we analyzed the free surface statistics for different experimental conditions. We noticed that the wave steepness increased for an opposing wind, hence being more prone to breaking, energy dissipation, or transfer to different length scales and to mixing. For only wind waves, we observed the formation of wave groups typical of this type of waves. We also studied the evolution over the phase length of the free surface elevation signals for different experimental conditions. We noticed a non-monotonic wave growth with height proportional to the phase length, with a sporadic reduction of the root mean square height due possibly to breaking from swell and an opposing wind. A non-uniform wave growth for only wind waves with an average height growth proportional to the fetch length with an exponent of 1/2, and a smaller height for swell and wind following conditions than for the other experiments. We also performed a frequency analysis of the free surface elevation signal to obtain the power spectra. From the power spectra, we noticed that the high peak component due to the paddle waves is higher than the mean peak of the wind wave component. And also, we noticed that the decay of the wind wave's tail is proportional to the frequency with a power of -6. In order to clarify the velocity analysis, it is helpful to focus on the triple decomposition technique applied to the signals. The velocity is assumed as composed by 3 components: a mean velocity obtained from the time average of the whole signal, a periodic or wave velocity obtained through a phase average of the signal at the net of the mean velocity, and a fluctuating component obtained after subtracting the mean and the periodic components to the whole velocity. The mean velocity represents the current developed in the flume and is due to several factors, including wind forcing, the finite length of the channel, and nonlinear regular waves features between trough and crest. In order to avoid bias due to alternation of water and air near the surface, we only consider measurements of velocity in the presence of water through a phasic average. The most evident result is for the horizontal component and shows values in the direction of the wind near the surface, while they assume opposite values towards the bottom in order to fulfill the mass conservation. We now focus the attention also on the turbulent kinetic energy in water, obtained by separating the turbulent velocity components through the triple composition technique described before. We notice that in the absence of the wind, the turbulent kinetic energy is almost null. Also, we notice that paddle waves and following wind show higher values near the surface, while in the presence of paddle waves and opposing winds, the turbulent kinetic energy reaches deeper waters. From the turbulent components, we can also evaluate the turbulent velocity correlations, which represent the Reynolds shear stresses and are linked to the turbulent momentum flux and energy transfer from air to water, or vice versa. We notice that all the terms show negative correlations near the surface, but only the correlation between the horizontal longitudinal component U and the vertical component W is significant and with an opposite sign far from the interface. Dimensional consideration can also be made for the problem studied. First, we find the relevant variables for the wind waves generation process and identify the fundamental variables to be the wind friction and the gravitational acceleration. With some simplification, we obtain 3 non-dimensional groups representing the non-dimensional wave height, wave period, and fetch length. We make use of fruit similarity to model the prototype conditions, reminding this choice distorts the velocity and the time scales, as well as the Reynolds number between the model and the prototype. It means that a transitional or laminar flow in laboratory could result in a fully turbulent regime in the prototype. However, bearing these limits in mind, we verify that our experiments encompass almost only turbulent flows, limiting the distortion effects of full similarity and sustaining the reliability of our results. In summary, we tested 4 different experimental conditions using stereo PIV, ultrasound probes, and a pitot tube to analyze the velocity in water and the free surface elevation. Furthermore, we made use of dimensional analysis to check the reliability of our results. Our results show the different behavior for the different paddle waves and wind conditions tested. For the free surface statistics, we noticed that we have a higher wave steepness in the presence of paddle waves and opposing wind. Related to the wave growth, we also noticed that for paddle waves, in the presence of the wind, both following or opposing, the wave growth is bigger than in the presence of only wind conditions. From the frequency analysis, we observed wind waves tail decay proportional to the power of -6. Related to the velocity and correlation analysis, we analyzed the mean, the periodic, and the fluctuating components. From the turbulent kinetic energy, we observed different behavior for the different conditions tested. In particular, we noticed that the turbulent kinetic energy is bigger near the surface for the paddle waves and the following wind, while it takes bigger values more in depth if related to paddle waves and opposing wind. Finally, we noticed the importance of the correlations, turbulent correlations between velocities near the surface, which represents the stresses and hence the energy transfer from air to water. I really thank you for your attention and invite you to write to the mail below if you have any concerns or doubts. Thank you again.